In this lesson, we're going to examine a new counting technique called combinations. A combinations is an arrangement of objects, like a permutation, except order does not matter. That's our key here. So for example, if we had we're dealing a deck of cards out, it doesn't matter what order you got the cards in. What matters is what you have in your hand. So if you got a 2, then a 3, then a 4, then a 5, that could be considered the same as a 3, then a 5, then a 4, then a 2. Order doesn't matter. So we now have to tell apart two different things. Permutations, where order does matter. You're filling specific spots or positions. So for instance, first, second, third, or president, vice president. And a combination, which order does not matter. We're selecting a group. We're making a committee. We're figuring out different things where the order doesn't matter. That's going to be kind of a challenge to tell apart at times. So we'll look at an example here. In the first example, how many ways could Al, Bob, Chuck, Dan, and Ed finish first, second, or third? So just to make a list to make our life a little bit easier. So Al comes first, Bob, then Chuck, or Bob, then Al, then Chuck, or Chuck, then Bob, then Al, and so on and so on. Well, I can tell who came first, second, and third. It's obvious. Al came first, then Bob, then Chuck. This is a permutation. There's 5 people. We want to fill 3 spots. We're using our P button, and we get 60 different combinations, or 60 different arrangements. However, if we look at part B, in how many ways could these same 5 people finish as one of the top 3? Well, if they're the top 3, then these things are considered exactly the same. They're considered identical items. So that's no longer a permutation. That's a permutation with identical items. And how many things are the same? Well, C, B, and A are all considered the same. They're repetitive, repeated, identical items. We've got to divide them out. And we get 10. And now, it's not hard to think of this, how many items, how many spots, and how many identical things, but there's a slightly faster way of doing this. So if you come across a permutation with some identical items, we can do that as a combination. And here's our formula. So if we have n distinct objects, and we want to select R from them, we can take our permutation idea, NPR, and divide out the common things. And if we do that, and this is just notation here, you don't stress too much about it, we end up with a combination, NCR, and that's a button on your calculator. Probably located right next to the NPR, or maybe above or below it. Okay, there are 3 different formats this notation could take. Our standard will be NCR, but you might also see the C, NR, or fancier books use N over R. And it's not a fraction, and it's just a way of showing a combination. So let's give it a try with our calculators. Okay, so let's try our calculator. We'll try the ones on our calculator we can see here. So 5C2. If you do that, you should hopefully get 10. So it's 5 objects. We're choosing 2 at a time. We can do C71, which means 7 objects. We want 1 of them. Well, there's 7 different choices. Or 12, 6. And you should get 924. As I said, we use these notations interchangeably, but I'm going to use the first one 99% of the time, just to make life easier, so I can tell a combination apart from a permutation. Okay, so let's try a couple of examples here, how we can tell these are combinations and not permutations. So how many ways could you form a group of 3 letters from the alphabet? Okay, the key here is that it's a group. If I cannot tell order apart, as in I'm not asking for 3-letter words, because words, A, B, C is a different word than CAB. These are permutations, okay, where I can tell words apart. Groups are combinations. I don't care about the order. I just want to know what letters are in there. So this is 26, C3. You should get 2600. I'm going to try another one. Okay. I just want to point out that there are times where we can apply other counting techniques like the multiplicative principles. So if there's stages to your problem, you might have to do a combination followed by another combination. Okay. So for example, we have a committee. It's formed with 3 men and 3 women. We have 6 men that have been nominated and 7 women that have been nominated. How many different committees are possible? A committee is a fancy way of saying group. I'm not asked to fill in a president and a vice president and a secretary and give them specific jobs. So this is a combination. But I need to select the men and the women. All the men, the group, there's 6 to choose from, and I need 3 of them. The women, there's 7 of those, and again, I need 3 of them. And we know the idea of and means I need to multiply. So we can combine combinations with multiplying. And hopefully you get 700 if you do that one. You could also combine them with the additive principle. If we have cases, things that are that are mutually exclusive, they can't happen at the same time. We think of the word or. Well, we can add those things. So for instance, we have a bin containing 8 red bean bags and 6 blue. And how many ways could you get red or blue? Well, I don't have any bean bags that are both red and blue, so no overlap. These are mutually exclusive. My red ones, there's 8 of them. I need to choose 3. Again, it's a group because I don't care about the order of these bean bags. I can't tell them apart, in fact. They're identical. Same thing for blue. I need 3 of those. And it said or, so I'm going to have to add. And if I do that, I should end up with 1,050. Okay. Okay, so let's go to the standard typical question. This is our big question. We've got parts and pieces we're going to look at. And as I said, this is our typical question. We do a quiz. This is the question you're going to get in your quiz. So we have a committee. It's the fancy way of saying a group of students and teachers being formed to study the issue of student privileges. We have 15 teachers and 18 students who have expressed an interest in being on the committee. We want to make a 5-person committee. And now we've got some conditions. Part A, there are no restrictions. So anybody is allowed to be on this committee. It doesn't matter if you're a student or a teacher. As long as you're a person, you can be on it. So altogether, we have 15 teachers and 18 students, which makes 33 people. I can choose any of those 5 to be on my committee. It doesn't matter what their roles were. I just combine them. So I end up with 237,336. Okay. What about, I'll try part B here. The committee must be all teachers. Well, I mean, they can't choose from the students anymore. I'm only choosing from the teachers. There's 15 of them, and I need 5 of them. If we try that, we get 3,003. The committee must have 3 teachers and 2 students. Of my teachers, I have 15. I need to choose 3 of them, and I'm multiplying here. Students, there's 18, and I need 2 of those. And we should end up with 69,615. And these hopefully seem pretty standard so far. Let's take a look at D. The committee must not have more than 3 teachers. Now, this is a cases question, because it doesn't tell us specifically how many teachers we have, as long as we don't have more than 3. So the way I like to do these questions is I like to set up a little table. So teachers, how many could I have? Well, so they can't have more than 3. So I could have no teachers, or 1 teacher, or 2 teachers, or 3 teachers. And it implies, without saying it, because we need a committee of 5, that if I have no teachers, there's 5 students. If there's 1 teacher, there's 4. 2 makes 3, and 3 makes 2. So these are the different combinations of teachers and students I could have. To pick the teachers, however, I have to go back to the idea that there's 15 teachers and 18 students who I can choose from. So these are going to be 15 choose. This is going to be 18 choose. And any teachers and students, I'm going to have to multiply. So these are all going to be the same. 15 choose, times, times, times. 18 choose, times. Okay, and if we do this, our numbers come out to 8,568, 45,900, get these 4 different things. Now these are each cases, mutually exclusive cases. In other words, the idea of or. There's no teachers and 5 students, or 1 and 4, or, which means I need to add up each of these cases. And if we do that, we end up with 209,763 cases where there are no more than 3 teachers. All right, last one for this question, part E here. You must have at least 1 teacher. Okay, 1 teacher. So, teachers and students, at least 1. So I could have 1, which would imply 4 students, or I could have 2 and 3 students, or 3 and 2 students, or 4 and 1 student, or 5 and no students. These are all possibilities. Now, that's a lot of cases to go through. So here's a good idea for us. What if we use our indirect method? Get rid of what we don't want. We're not allowed to have the case of no teachers and 5 students. If I take my total and I get rid of the case of no teachers, I'll be left with the case of at least 1. Like this table that we just made here shows every possible combination of teachers and students. So if I get rid of this 1, I'll be left with all of this without actually having to calculate them all. So let's look at that first case. No teachers, that's 15, choose 0 times 18, choose 5. Okay. Our total, well, we did that in part A. That was 237, 336. If I subtract this one case, that one case of 15 choose 0 times 18 choose 5 comes out to 8568. And if I get rid of those cases, I'll be left with the at least 1, which is 228,768. Okay, so that indirect method is another counting technique that's come back. Now, theoretically, I suppose you could have done this previous question that way too. And you could have gotten rid of the case of 4 teachers and 1 student, or 5 teachers and no students. And that actually would have been faster, and it does work. But it's kind of your choice which way you want to do this, direct or indirect. All right, I got 2 little examples left for us. Let's take a look at them. There are 17 people at a party. Each person shakes hands with everybody else. How many different handshakes occur? Now, we're not going to repeat handshakes. Once you've shaken hands with somebody, you're done. But if you stop and think about it, we already have 2 people shaking hands. In other words, we're making groups of 2. There's 17 people. The order they shake hands in doesn't matter. We just have to make groups of 2. So if you want to know how many handshakes there are all together, we can use a combination. Here's 136. Okay, last one. How many ways can 16 people be assigned to a 5-person car, a 4-person car, and a 7-person van? So what do we got to do? We've got to fill these spots. Does it matter what order they go in? No, it doesn't matter what seat you're sitting in, or even what vehicle you're in. You just have to get into a vehicle, right? So let's pick the 5-person car to fill first. We have 16. We need 5 people for that car. But once we filled that car, we no longer have 16 people. Some people are sitting in the car, right? They've gone to the party already. So what do we have left? We have 11 people, and we're going to fill the next car. And don't forget, we're filling one car and the next car and the third thing, the van. Again, we've put people in the car, so there's only 7 left for the 7 spots in that van. So if we do the math, we end up with 1,441,000. Now somebody out there is going to say, well, what if you want to fill the car first, the 5-person car? You don't have to. Because order doesn't matter, and this is a totally different way of doing this question. So I'm using the word or, but I'm not adding things together here, okay? I could have filled the van first. I could have said, oh, let's do 16 choose 7, which would leave me 9 people. Let's do the 5-person car next, and then I'm left with the 4-person car. I don't really actually choose this. That part fills itself in, right? There's 4 people in 4 spots. But if you try it, it turns out that you end up with the exact same number because it doesn't matter about order. Order is not important when we look at combinations. Okay, some questions for you guys to try. Try these. As usual, the more practice you get, the easier they'll be. If you're stuck on some, come see me and we'll look at them together.